So, my dear students and dear friends, in this video we'll be talking about Hermitian operators, and it's quite evident that these Hermitian operators, I mean, in quantum mechanics, these Hermitian operators, uh, they are a special class of operators that play a crucial role due to their physical significance and mathematical properties. And if we go with the definition, suppose we have an operator, say a cap, and this operator on a Hilbert space, we call it Hermitian or self-adjoint if it satisfies a dagger equals a cap. Now this is called dagger. What this a dagger that I have noted down here, it denotes the Hermitian. It denotes the Hermitian conjugate or adjoint, Hermitian conjugate of the operator a cap. The Hermitian conjugate of an operator is obtained. This is obtained by taking the transpose and then the complex conjugate of the elements in a matrix. We will discuss it in detail as we move on, but here we will try to attain a state of definition of Hermitian operators and talk in generality about the properties of these operators. So the point is quite simple. If a dagger is equal to A, provided A is an operator, then this operator is a Hermitian operator. And we understand that this dagger means that if we have a matrix element, say 1, 2, 3, 4, we have to take its transpose and then the complex conjugate of each element in this matrix, if they are the complex numbers. If they are not the complex numbers, then you will not have the complex conjugate. So for complex numbers, for complex functions, we will have a complex conjugate. So if there exists the transpose and the transpose and the complex conjugate of transpose equals the original operator, then this operator is referred as the Hermitian operator. Now, talking about the properties of these Hermitian operators, which we will tackle mathematically later on, but here we will try to give the textual approach of the properties of these Hermitian operators. The first point I would like to talk about is the real eigenvalues. Real eigenvalues. Now, these Hermitian operators that I talked about, these Hermitian operators, they have real eigenvalues. This is important in quantum mechanics because the observable quantities that we have here, say position, energy, momentum, they are associated with corresponding operators. They are associated with Hermitian operators. And the eigenvalues of these operators correspond to the possible measurements or the outcomes. And these outcomes of these Hermitian operators that are acted upon the state vectors lead to the real numbers. So here what we obtain is the real eigenvalues. The next important point is the orthogonal eigenvectors. Orthogonal eigenvectors. Now, what does it mean? The eigenvectors the eigenvectors of these Hermitian operators corresponding to different eigenvalues. Suppose we have different eigenvalues, say E1, E2, and so on and so forth. And corresponding to this eigenvalue, I'll have an eigenfunction, or you may call it an eigenvector, say psi1, psi2, and so on and so forth. These eigenvectors are orthogonal. That means they are perpendicular to each other. And this property allows us basically to diagonalize the Hermitian operators. in terms of an orthonormal basis of an eigenvector. And then is that the diagonalization. And what's this diagonalization? These Hermitian operators can be diagonalized. This means that there exists an orthonormal basis in which the operator can be represented by a diagonal matrix with its eigenvalues as the elements of the diagonal of that matrix, say A1, A2, and A3. And suppose we have position operators. For position operators, then we have momentum operators, and we have Pauli's matrices. We have Hamiltonian operators. These are Hermitian operators. And position, if I talk about position first, in quantum mechanics, position operator, say x cap, in one dimension is a Hermitian operator. In the position representation, it's represented by x cap acting on some wave function psi of x. And so if it operates on a wave function psi of x, we have x psi of x. And in matrix form, if we were to discretize, I mean, if we want to have discrete space, the position operator would be a diagonal matrix with the position values along the diagonal, where you are able to quantize the space, say, in one dimension. So the diagonal positions that we obtain in a matrix, they are representative of that discrete patches of the space. So this matrix is Hermitian since its transpose is equal to its conjugate. And similarly, we have a momentum operator, and we have momentum operator. And this momentum operator is symbolized as p cap. And the momentum operator in one dimension is also a Hermitian. It's a Hermitian operator, following the same condition. And in the position representation, we can write down this momentum operator in terms of its position. And in position, we can write down this p cap is minus I h cross 2 pi 2x. And then we have Pauli's matrices. We have Hamiltonian operator. Now we want to prove here in this video that these operators are Hermitian operators. And for the proof, I will start with the position operator. Position operator. So I have a position operator x cap, and this position operator acts on a wave function psi of x. So x cap psi of x leads to x psi of x. Now, to prove this, let us write down this position operator in terms of the expectation value. So in general, what we have to prove basically is we have to prove that if I have a state phi x cap of psi, this is equal to x cap of phi and psi. And this is quite evident to us that what it means. So if we are able to prove that this inner product is equal to this product, we can say that position operator is a Hermitian operator. And we can write down this expectation that this phi of x cap and psi as the integral minus infinity to infinity phi star. This is the bra, this is phi star of x, then we have x cap, and then we will have the psi of x, and then dx. So this is my phi, this is bra of phi, and ket of x cap of psi. So we can write down this in integral form like this. That should be the case. Now, taking on x cap phi and then psi. How can we write it in terms of integrals is minus infinity to infinity. Then I have x and phi of x, the star of these two. And then I have psi of x dx. And since x is a real number, so it will come up as the real number. And what we will come up with is minus infinity to infinity, then phi of x of star x psi of x dx. So if we compare these two, this and this, we are here. So clearly this is equal to this. And what does it mean? It means that the position operator is a Hermitian operator. X cap that we have chosen here as the position operator is a Hermitian. Now let's go to the next, that is momentum operator. Momentum operator. So momentum operator, I wrote down it, that is minus IH cross dou by dou x. So I have written down the momentum operator in position representation. And what I have to check that this operator is a Hermitian operator. So for that, what I have to do is that I'll take the state phi p psi. So I can write down this as minus infinity to infinity. So for phi, I will have phi star of x. And then I have p cap. So for p cap, I'll be using this. This is minus IH cross dou by dou x. And then I have psi. So psi should be here, psi of x. And then close it and then dx. And we can integrate by parts. So if we integrate it by parts, what we will get is it is minus IH cross, then we will have phi star of x, psi of x, minus infinity to infinity. Then we will have minus integral minus infinity to infinity dou 2 phi, no, it shouldn't be 2, dou phi star of x by dou x, psi of x and dx. Now, if we assume boundary conditions here, and what is happening here is that this phi star, this term, this phi star of x and psi of x, it goes to 0 at infinity. So at infinity, this product goes to 0. That means this whole term vanishes. So we can write down that the phi, the bra of phi p cap psi is, what is it? This will be IH cross integral minus infinity to infinity, then dou phi of x star by dou x and psi of x dx. Right. And what we would like to do now is we would like to compare this result with bra of phi and p cap of psi. No, it shouldn't be like this. It should be p cap of phi and psi. So how can we write down this in terms of the integrals? So we can write down this as minus infinity to infinity, then minus, so for this p cap we have minus IH cross dou phi of x star by dou x, then multiply, and I think this whole thing is a star. Why am I keeping it here? So star is here, and then we will have psi of x for this and dx. And the complex conjugate of iota will give us, it's going to give us IH cross minus infinity to infinity, then dou phi star of x by dou x, then psi of x and dx. And we can compare these two results that we have obtained here. So comparing this and this, what we obtain this is equal to this. So we have proved that P is a Hermitian. What does that mean? That means the bra of phi, P cap of psi is equal to P cap of phi and psi. So this proves that the momentum operator P cap is a Hermitian operator. Now, moving on, let's take on the Pauli's matrices. Pauli matrices. Now, we have predefined Pauli matrices. We have sigma x, and sigma x is 0, 1, 1, 0. We have sigma y. Sigma y is 0 minus iota. Then we have iota and 0. And then we have sigma z, and that is 1, 0, 0, minus 1. So what we have to do here is that we have to prove that these Pauli matrices, they are also Hermitian. And proving Hermitian means the dagger of that operator must be equal to the operator. So if that's the case, then we will say that the operator is a Hermitian operator. Now, the first is sigma x. And I would like to calculate its sigma dagger. So what is sigma x? Sigma x is 0, 1, 1, 0. Okay, I have to calculate its dagger, and we can see they are just numbers, so they won't. We have to transpose this matrix, but it won't have any complex conjugate because we are only dealing with the real numbers in sigma x. So if I take its transpose and then take its complex conjugate, that's going to give me 0, 1, and 1, 0, the same thing, which is sigma x. So it's proved that sigma x is a Hermitian operator. And the second case for sigma y, and what is sigma y is, that is 0 minus I, then I and 0, and we have to take its dagger. So in doing so, what we have to do, we have to transpose it. So you will have 0 and iota and minus iota and 0. And now we have to take its complex conjugate. So when we take its complex conjugate, we'll get 0 minus I, then I and 0. So what is this? This is sigma y. So we can see that sigma y is also a Hermitian operator. And same thing is true with sigma z. And we can obtain the same result for sigma z. So we can say that sigma x, sigma y, and sigma z, they're all Hermitian operators. Hermitian operators. Now, Hamiltonian, and this is another important tool of long range of quantum mechanics. This Hamiltonian operator is Hamiltonian operator. And what we want to prove that this Hamiltonian operator is also a Hermitian operator. And we better know that h cap is minus h cross square by 2m dou 2 by dou x2. This is our Hamiltonian operator, and we need to show here actually the expectation of this Hamiltonian operator. I mean, the product, the inner product of phi h cap psi is equal to h cap phi psi, as we did in case of the momentum operator. The same thing we have to do here for the Hamiltonian operator, where we are actually taking the dagger. We are taking the dagger of this operator, and And what we are going to do is we will first calculate this, and then we'll calculate this, and when the results will be same, then we will be able to say that the Hamiltonian is a Hermitian operator. So we'll take on the left hand side first. So the phi and h cap of psi. I can write down it in integral form minus infinity to infinity phi star of x, then for Hamiltonian minus h cross squared by 2m dou 2 psi by dou x2 and then dx. Now integrate this by parts. So on integrating by parts, what we'll obtain is this. It's the same kind of thing. We will obtain phi star of x and dou psi of x by dou x from minus infinity to infinity, and then we'll have minus integral minus infinity to infinity, then dou phi star of x by dou x, dou psi of x by dou x dx. Now, using the same boundary conditions as we used in case of the momentum operator, what will happen, this term is going to vanish, and if this term vanishes, you'll be left with a single term over here, right? And so what will be over phi h cap of psi? This will be minus will become plus, so this is h cross cap by 2m integral minus infinity to infinity, then dou phi star of x by dou x, then dou psi of x by dou x dx. This is one result. Now we have to compare it with another result. So what's that? So that is h cap of phi and psi, the inner product of h cap of phi and then psi. So in this case, what we'll obtain is we will have integral minus infinity to infinity, then minus h cross squared by 2m dou 2, it has to be phi of x by dou x2. This whole has to have a star on it, then psi of x and dx. And that's quite evident. So so what we will obtain here is we will obtain h cross squared by 2m integral minus infinity to infinity dou phi star of x by dou x, then dou psi of x by dou x, and then multiplied by dx. So we can see immediately, we can see that the result for this term and this term is same, and thus we can say that phi of h cap psi is equal to h cap of phi and psi. So what it proves automatically is that the Hamiltonian operator is a Hermitian operator. So these are some of the important results that we have obtained in this video, and where we have tried to prove mathematically that these operators like position operator, momentum operator, then Hamiltonian operator, these operators are Hermitian operators, and we proved that the Pauli matrices, the Pauli matrices, they are the operators, and these operators are also Hermitian operators.